Good morning, everyone. So, welcome to another session of image processing. Myself, Dr. R. Sudhir Babu, Associate Professor, the Department of Electronics and Communication Engineering, G. Pullareddy Engineering College, Autonomous, Kurnool. So, the last class we had discussed about the digitization process of an image. So, how we'll apply the concept of sampling and quantization in order to convert analog image into a digital image. Today, we'll see how we represent a digital image in the matrix form. So the process of sampling and quantization results a digital image f of xy, which is a two-dimensional matrix of real numbers. Okay, so a two-dimensional matrix of real numbers. Okay, the range of numbers. The range of numbers in the digital image basically depends on quantization process. The quantization is nothing but the digitization of grayscale. So if the grayscale is divided into 8 levels, so the numbers that you'll be getting will be 0, 1, 2, 3, 4, 5, 6, and 7. So 0 is black intensity and 7 is white intensity. So in the quantization, in the sampling and quantization process, or in the basically digitization process, if the grayscale is divided into only 8 levels, then the matrix, 2D matrix that we get in the digitization process will contain the values only from 0 to 7. So in each row, the number of values will be between 0 to 7. So depending on the intensity of the pixel at that position. See, after the digitization process, each element of the two-dimensional matrix is called pixel. So each element of this 2D matrix is called pixel. And the pixel will have an intensity or grayscale, or sorry, gray level that represents intensity of the pixel at that particular position. So the pixels will be having the values in this range if the grayscale is divided into 0 to 7. For example, so let me give you a simple 3 by 3 image. So assume that in the sampling process, we took 3 rows along x direction and 3 rows along y direction. So we get a 3 by 3 image. And the values, and we assume that the grayscale is divided into only 8 levels. So pixel values will be between 0 to 7. So the image created will be having the pixel value something like this: 4, 7, 3, 0, 1, 6, 5, 4, 2. Assume this. So here, this is the first pixel in the image, this is the second pixel in the image, this third pixel in the image. The pixel with the value 4 actually represents an intensity, something here. So this is at the middle of the grayscale. So this could be a shade of gray or a bit dark shade of gray. And the pixel with a value 0 will fall here in the grayscale. This represents black pixel. And a pixel with a value 7 will fall here in the grayscale, which is basically a white pixel. Okay, right. Right. So the values in a two-dimensional matrix, the pixel values in a two-dimensional matrix completely depends on the digitization process. If in the digitization process, if the grayscale is divided into, say, 16 levels, so in this case, the grayscale would extend from 0 to L minus 1. Number of levels are 16. So 0 to L minus 1 is 15. So this is the grayscale. So the pixel values will range from 0 to 15. So if you take an image f of xy, where the number of rows and columns are only 3 by 3. So now since the number of grayscale is divided into 15 levels, so pixel can have the numbers from 0 to 15. 0, 1, 7, 6, 4, 12, 7, 3, 9. Okay, now here the pixel value 0 represents black pixel, and the pixel value 15 represents white pixel, and the values between 0 to 15 represents the different shades of grays. And if the number of gray levels are 32, then the grayscale will be extending between 0 to 31. So pixel values in an image will be between 0 to 31. If the number of gray levels are 64, grayscale will be extending from 0 to 63, and so on. So if a number of gray levels are 256, then the grayscale will be extending between 0 to 255. The value 0 represents black pixel, and the value 255 represents white pixels, and the values between 0 to 55 represents different shades of gray. For all practical images, then the grayscale is divided into 256 levels. So pixel values will lie between 0 to 255. Okay, right. So the result of sampling and quantization, your digital image is simply a two-dimensional matrix of numbers. Two-dimensional matrix of numbers which will range in the grayscale, and the number of gray levels depends on the quantization process, right? So here we'll discuss one terminology. So number of gray levels L will be always powers of 2 power k. For example, L is 8, so this is 2 power 3. L is 32, it is the 2 power 5. L is number of gray levels are 256, it is 2 power 8, and so on. So the number of gray levels are always powers of 2. So this convention is just followed in the digitization process in order to simplify the design process of the hardware. Okay, so which will be used to convert analog images into digital images. So finally, your two-dimensional image is basically a 2-dimensional matrix of real numbers, where at each pair of coordinate you will have one pixel, and each pixel will have a value like 75, something like that, and this value represents a particular shade of gray, and each pixel will have a specific position, row and column number, and the number of rows and the number of columns are generally represented as m by n. M rows, n columns. The number of rows and the number of columns, that depends on sampling process. So number of rows, so how many number of rows that we take along x direction in the digitization process, and each row is divided into how many number of samples, that is the sampling in y direction, that represents n value. So the m number of rows and the number of columns depends on the sampling process, whereas the pixel value or the number of levels in the grayscale depends on quantization process, right? So now we'll see the coordinate convention. So f of xy is a 2D matrix. So the first pixel coordinate is 0, 0, second pixel coordinate is 0, 1, third pixel coordinate is 0, 2, and so on. So the number of columns, if you assume n, so this is n minus 1. The second pixel 1, 0, f of 1, 1, f of 1, n minus 1. So m rows, if you assume, so f of m minus 1, 0, f of m minus 1, 1, and so on, f of m minus 1, n minus 1. So this is the standard coordinate convention for a m by n digital image. where each coordinate will be having one pixel with a particular value or a number that represents intensity of pixel, intensity or gray level of a pixel at that point. Yep. Okay. Right. So here we'll see one terminology. So I said the number of gray levels are always 2 power k. So if a number of levels are 256, so this can be written as 2 power 8. If number of levels are 8, this is 2 power 3. So in a pixel with 8 gray levels, the pixel values will range between 0 to 7, whereas the image with where grayscale is divided into 256 levels, the pixel values will range from 0 to 255. So to take an example, f of xy, where the number of levels are only 8, 3, 4, 6, 1, 2, 7, 0, 1, 4. This is a 3 by 3 image where the grayscale is divided into only 8 levels, and these are all the pixel values. See, all these pixel values are, even though it is in the matrix form, and if you want to store this image in the computer, we cannot directly store these numbers into computer. So we need a kind of translation from, these are the decimal numbers. We cannot store decimal numbers directly into the computer, so we need to convert that into the zeros and ones, isn't it? So only in the binary form we store the computers or the memory. In the memory, data will be stored in the form of only ones and zeros. So all these decimal numbers has to be translated into binary. Now the point is how many number of binary bits are required to represent any one of these numbers in this image. So in this image, so we have only the pixel values in the range 0 to 7. We have total 8 pixels or 8 intensities, 0 to 7. So if you want to represent any one of these numbers, the number of binary bits required are only 3, because so if you want to represent 3, so this is 0, 1, 1. If you want to represent 7, this is 1, 1, 1. If you want to represent 2, 0, 1, 0. If you want to represent 0, will represent 0, 0, 0. So the numbers from 0 to 7 can be represented using only 3 binary bits, 0, 0, 0 to 1, 1, 1. So the L is equal to 2 power 3. So 3 actually represents number of binary bits required to represent each pixel. Right. So in this case, this image is basically called as a 3-bit image. So in a 3-bit image, so the number of binary bits required to represent each pixel is only 3. So here we have the quantization process where the number of gray levels are divided into 256 levels. Now we have numbers from 0 to 255. So if you want to represent all these numbers using binary combination, so we need 8 binary bits, 0 to 255. 0 to 255. So if you want to represent these numbers, we need the binary combination or number of binary bits 0, 0, 0, 0, 2, 1, 1, 1, 1, 1, 1, 1, 1. So in this case, the image produced is called a 8-bit image. 8-bit image. Now you'll see the storage requirement. So number of bits required. So you have a digital image f of xy of size m by n, m rows and n columns, and this, assume this is a k-bit image. So k actually comes from number of gray levels, 2 power k. So if number of gray levels are 8, this is 2 power 3. So k is 3. So assume this is a 4 by 4, k is 3-bit image. So in a 4 by 4 image, we will have total 16 pixels. Since it is a 3-bit image where grayscale is divided into only 8 levels, pixels will be in the range 0 to 7. So in order to represent every pixel, we need only 3 bits. So total number of pixels are 14. So let me take example. F of xy is, it is a 4 by 4 image. 4 rows and 4 columns. Pixels are 1764, 3210, 104A46, 2254. This is an example of a 4 by 4 3-bit image. 3-bit image. Right. So if you want to store this image in the computer, how many number of binary bits are required? Number of binary bits required. So we need to store all 16 pixels. So 4 into 4, this is it. And in order to represent each pixel, we need 3 bits. So 4 into 4 into 3. So 48 bits are required to store this 4 by 4 3-bit image in the computer, or 48 bits of memory is required to store this image in the computer. So number of binary bits required, or it is also called memory requirement. Memory requirement. So if you take the general syntax, or the general, if you take the general numbers, or the variables like m and k, so the number of bits required are m, number of rows, number of columns, into k, number of bits. So the storage requirement is m into n into k. So let us use a different storage requirement. S is m into n into k bits. That's it. So this is how a digital image is represented, and how we can estimate the storage requirement for a digital image. Okay, so we'll stop here and we'll continue with the next topic in the next session. Thank you.